So good morning, everybody, and welcome to this event here at AI Sweden, where we are going to take you through the latest advancements in the Edge Learning Consortium and decentralized learning here that we've been working on for the last year. My name is Mats Nordlund. Today is the 25th of April, 2023, and we have an exciting program. We're going to essentially bounce on a number of advancements that we've done here, and then after that section, we are going to, for the people who are here in the room with us, we're going to have a poster session where you get to network and meet some of the people presenting here today. As an introduction, I'm going to have my good colleague and good friend here, Helena Theander, who is leading the data factory here at AI Sweden with me. And she is going to give us an introduction to what is AI Sweden. So give you a sense for where you are.
Thank you, and welcome to AI Sweden. We have been around for 4 years with the mission to accelerate the use of applied AI for the benefit of the society, our competitiveness, and everyone living in Sweden. That is what we do today and every day. And we are a national center. That is why we both are here present today in Gothenburg, but also broadcast it so that wherever you are in Sweden and our international friends as well can participate and learn what we have been doing. We are a neutral non-profit platform, and that is a prerequisite for private and public sector working together. And today you will see a lot of examples from both public and private sector, which I think it's what's needed to fulfill our mission. We are funded by Vinnova, the innovation agency of Sweden, and also from all our partners. And all of our partners, which is more than 100 partners, are contributing and engaging in everything we do. And that is partners from academia, from public sector, from global techs, corporates, startups. And what I think is mainly the most fantastic is that they represent different sectors. And today you will see examples from when we use more or less the same technology in healthcare, in cybersecurity, in automotive, in space and finance sector. So that is really a benefit when we can have this interaction from this cross-disciplinary plethora of different organizations and individuals. Our mindset is investing together, sharing with many, and sharing is exactly what we are going to do today. And we collaborate in anything we do, whether it's an event, a decentralized project, or building the infrastructure that we have here. The Edge Learning Lab, where we lead the way with speed and boldness. And I think this lab is a good example of this. Within just 1 or 2 months, we went from nothing to a lab which functioned. The Edge Learning Lab, which also is a world-leading lab, meaning that we set the direction and we go there with speed and boldness. Now I leave back to you to get to know even further on what decentralized learning is and what do we actually do in this lab.
Thank you so much, Helena. And what I'm going to do is I'm going to start off with a short video that we had made last fall to introduce you all to what is decentralized learning, to make sure we're all on the same starting point. So with that, I'm going to start this video.
To train AI, you need a lot of data and repetition. Take this hospital as an example. Data from devices, journals, decisions, and tests can be used to train AI and save lives. But data from only one hospital is way too narrow to train a good AI model, and we're not allowed to move or share data from different hospitals. There are 3 main reasons why we can't move or share data. Regulations on data transfer or commercial confidentiality. Large volumes of data make transfer and storage costly and complicated. Opinions, activities, or other sensitive information can jeopardize people's privacy. Decentralized learning solves this. Now we can do things with AI that just weren't possible before, without compromising, sharing, or moving data. We move the AI to the data, train on different local data, bring back only the insights from training. Merge all the insights to form a better AI model and send that back out for further training. Cars can learn from each other and make traffic safer. AI and satellites can learn to better spot forest fires, flooding, or deforestation. Back at our hospital, better AI models can make better diagnoses and save lives. This is why we built the one-of-a-kind Edge Learning Lab here at AI Sweden, together with our partners. In this lab, we learn together and accelerate innovation by trying new ideas and developing techniques for decentralized learning.
So that gives you a short overview of the technology we are working with here and developing together with our partners. I'm going to take you on a very brief historical journey. How did we get here and why do we have this lab? And then talk about how are we developing this going forward. So the first idea of setting up our platform, as Helena described it, AI Sweden, came in 2017. So that's almost 6 years ago now. When we were discussing here, how should we set up a national platform for developing AI here, and together with partners, universities, public sector, industry, and so forth. And how can we do something that's not just copying what everybody else have done? And we quickly came up with this model here, where we have what we call a research arena, which is not just a center in one place, but an arena as part of the whole country where we can have presence in many locations. And co-locating that with a data factory so that we can both work on development of algorithms and models, as well as working on the development of the hardware and the infrastructure needed. And then we can have the researchers, and you will see that today, who work on algorithms and models. They can talk to the infrastructure development and get ideas, see what's possible, but also influence the development of infrastructure and tools. It's much of the same ideas you have in other fields. For example, in physics, we could see CERN, the particle physics center in Europe, where you have engineers working with physicists, talking to each other, learning what can you do, what can you not do, and how to get ideas from each other. So we thought we'd try to replicate that here. So this was our idea of how can we run faster here in Sweden than you can do in a location where you have only a AI center without having a co-located data factory. So set up to do that, and we thought, how should this data factory work? There was no model to look at. There was nobody else who'd done this. So we came up with two strategies, and these are the ones you see here. We said we should complement things that are done in the country so that we don't do the same. So we saw large investments done by, for example, the Wallenberg Foundation in the new Berzelius Superpod training cluster in Linköping. We saw universities investing in similar or compute clusters. So we said, let's do something that complements that. And let's do something that, as we could see in the previous picture, is valuable both to the people who want to use it, as well as the organizations and people who develop this technology. And the goal should be to make innovation possible for both, to reduce risks, especially if you're investing in expensive equipment, you can test it here. Reducing the barriers. If you reduce the risks, people are more willing to invest. And that way, having all these in place, we think that developing or accelerating the development of AI will take place. So back to the model Helena showed, where we invest together and share with many. This here represents AI Sweden, where you invest together. We can work together between organizations here and take it all the way to a prototype or demonstration unit. We can't take it into a commercial development because we do have support, as was acknowledged here, by Vinnova and other state sources. So we can go to the limit here that's allowed within the state funding rules. And then partners have got to know each other, and then they can go out and do commercial agreements and so forth out here. So we see a very exciting and dynamic environment where we have companies collaborating, learning together, learning with academia and with public sector. How can this be done? And you will see examples of how that actually has happened for real here today. Helena was pointing out leading with speed and boldness is one of our key values here. And this here shows how we developed the Edge Learning Lab, which was put in place in accordance with the previous slide where we said, let's do something that complements. So we said, we learned about federated learning. We learned about some of the research that was done in other countries. And we said, well, nobody has a lab to explore this that's available to a broader audience. So we said, let's see if we can build that with our partners. We had 3 partners. It was Hewlett-Packard Enterprise, Volvo Cars, and Sensact, who said, well, we are very interested in setting something up. So they donated equipment and said, we'll put this in place. And I'll acknowledge Mats Moberg here, who was head of development for Volvo Cars at the time, one of the key persons behind getting this to happen. And on the middle of December 2020, this is what the lab looked like. About a month later, it was up and ready to go. And we opened it on the 27th of January. And this was only possible because the way that partners stepped up and said, we'll donate the equipment, we'll donate the manpower to make this happen. And then Vinnova stepped in and said, okay, given we have this lab in place, we'll help you to accelerate the establishment. And we were able to get some funding to match the donations, and that way we could hire some people to work in the lab and develop the technology further. So in September 2021, we were running things across Europe, big hackathons, and we were getting more and more interest in the lab. And we have today a lab with equipment that's been donated that's in excess of about 50 million SEK, so about 5 million euros in total we have in the lab. And it will be open for you to visit later on this morning after the poster session if you want to see it for real. It's upstairs here. So this demonstrates that if we invest together with speed and boldness, we can get something where you can share with many. That's very straightforward how to do it. And the way we have here in Sweden, the ecosystem with the companies and the funding agencies, really you can make magic happen here that is hard to match. We have then, since we have a completely new model of a national center, we had to think about how to explain what we do here and how can people and organizations benefit from coming here. The best way to think about what we have is think of AI Sweden as a gym or an AI gym. So when you become a partner here, you buy a partnership membership. And that's like buying a membership in your gym. And just like at the gym, the more you come to work out, the stronger you get faster. So by coming here and engaging, that's how you build your strength. We don't sell anything. We don't build your strength. We help you. We have PTs, as we call ourselves, many of us. That is partner trainers here, not personal trainers. And some organizations send their people here on, and we'll come back to that, just to have some professional development also. They can be here for 6 months or 12 months or 18 months and work in this environment with colleagues from all over the country, all different application areas, and then go back to their organizations again with new knowledge. So think about this as an AI gym. We've started to get more and more interest from international partners, and we see quite a good work on the embassies here in Sweden, the foreign embassies. They go around and they scout what's going on, and then if they find something of interest, they typically send visitors that way to see what's being done here. So last year we had a number of very high-level visitors coming here. You can see here the King and Queen of Netherlands came. It was a very, very good visit, super competent, very good questions. They were hosted here by the Swedish King and Queen in that visit in October. We also had Prime Minister of Estonia came here to learn more about what we do, and Erna Solberg from Norway came just after she retired from being a prime minister. She came here now as the opposition leader to learn also what is done here and how can that be transferred. So we see a number of very good visitors coming, and that keeps us on our toes. We get really good questions from all of these. Some of them we have good answers to, some of them makes us think. So it's not only technical questions we get political questions and more of representation. How can we collaborate? How can we set up different ways to work together across nations? I'm now going to show a new little video. That's the first one, just to explain the technology. This one here was shown at Sweden Innovation Days. It was produced by Vinnova, and it just shows what people do here today and how they think about it. So with that, I'll start this short video.
What's unique about this lab is that it's an open sandbox for our partners. We want them to be able to go from an idea to proof of concept and gain the necessary knowledge to know what they should implement and how they should implement, so they can accelerate the use of AI. And what we do here is really facilitate various types of experimentation, testing, learning, new ways to fail, new ways to succeed. And we do that in a collaborative fashion. We say, invest together and share with many.
When it comes to AI projects, you also want to make sure that it scales. And you want to test something close by to where you are, where you have people, where you have equipment, and then you want to be able to distribute that maybe globally to all the other environments that you have. So I think that's one of the biggest winning themes of being here at the testbed.
Since we're a startup developing tools for edge learning, specifically federated learning, I mean, having an infrastructure like the Edge Lab is really invaluable. It's a place where we can test our software in real production-like environments and collaborate with some of the best enterprises in Sweden on this.
The technology we are exploring here solves a number of paradoxes that we've seen in traditional AI training. Traditional AI training, you have a data center somewhere, you send all the data there and you train on some large computer and you get your model at the end of the day. In edge learning, we move the algorithms to the edge, to cars, to satellites, to hospitals, and we use the compute power that's available out there. It's a lot less data we have to ship. We don't have to be concerned about sending sensitive data from the field back to a data center across country borders and so forth, and we actually train in the devices.
We see this as a game changer in developing autonomous driving software in the future.
A very exciting area that we are working on as well is space. So we have projects, for instance, where we are developing AI models on board of satellites in a federated fashion. This is relevant, for example, for Earth observations, where we aim at creating an alert about, for instance, forest fires.
It enables, for example, hospitals to collaborate around data that they could not do in the past. We now see interest from the financial sectors, the banks that have not been able to collaborate before to combat financial crimes. So it's absolutely changing or opening up things that haven't been available in the past.
I think the speciality around this lab is that it's actually not just multi-industry collaboration on paper, but in fact, I mean, if you take a look on all the logos, companies and customers involved, it is really a universal approach to AI development. And it is very thrilling to see how a community brings AI into life.
This lab is available wherever you are in the world. So we're seeing a large interest internationally for this lab.
And a lot of companies want to explore how far can we push it, and every year we see new possibilities opening up as the technology develops.
It's cutting edge, it's interesting, you get to meet a lot of incredible people who really know what they do and just see what's going on in technology and the future. Great fun, great fun. I love it.
So that's a little bit about where we are and how we are presented right now. And for the colleagues and our board and so forth who are working on this, we look at ourselves in the following way, and we give ourselves the following challenge. We feel very proud and happy that we have a lab that we can define as world-class lab. We see colleagues and organizations from around the world coming here wanting to learn. Some are sending us questions for how can they build a lab like this. Others are just coming here to work with us. And so we feel very comfortable and happy to say that we have a world-class lab. Now, that doesn't make you into a world leader. So the question that we challenged ourselves with is, how do you go from world-class to world leader? So the image here illustrates that by thinking in movie terms. So you can have a world-class film studio with all the latest equipment and all the fancy lighting and so forth. But how do you make yourself into Hollywood? How do you become Hollywood of edge learning? So to go there, we said, well, let's think about creating a consortium that is to focus efforts, to collaborate and use many of these strengths that we have and actually organize ourselves around that rather than having a fragmented set of projects that are being run, to actually have something that has some drive, has some force, and has some financing behind it to really have directions and go for the difficult problems, not just solving tomorrow's problem, but what is the long-term problems. We think that that would attract more thought leaders, it would excite people who are here, and it would also help transfer knowledge back and forth to industry. We'll get good challenges and we'll give good answers back, hopefully. So that's the background to the Edge Learning Consortium, and the consortium is what we are presenting from today. So you will see all the people who are working here, how that actually works together to take us to this place. So to build world leadership, we started off with the infrastructure. And as you could see from the beginning, the first direction we went in was into mobility. We had the automotive companies and one of the infrastructure providers, in this case, Hewlett Packard Enterprise, saying, well, let's build something we can do experiments on to learn how to do federated learning, decentralized learning in cars. Now, being located here at AI Sweden, it was colleagues from the healthcare side who said, well, this seems interesting to us too, because we have a similar problem. Our hospitals can't talk to each other, and we also need to share data. So we'd like to step in here and be part of this. So a project was formed with support from Vinnova called Decentralized Learning, and project started to work here, leveraging all this. And after not too long, we had a contact from European Space Agency, and they said, well, you know, what you guys do here seems to be highly relevant for what we do in Earth observation field. We have satellites, as you could see in that previous movie. Let's see if I can get this to work. Yeah. And this technology could solve some of the key problems in space where Earth observation satellites fly around, take pictures, and we have to transfer all these pictures to Earth to train and model. And that's a lot of data. Could we train it in the satellites instead, using the same technology? That would save us a lot of bandwidth transferring data up and down. So European Space Agency contacted us, said, could we do something here? And we wrote a letter of intent, which we're now putting in place on establishing a phi lab, the first phi lab outside the main organization at ESA's headquarters. We have a colleague from ESA here today who will show his part of the advanced research team from ESA, Pablo here. He will show some of the work they've done and how that is relevant for some of the other fields. More recently, one of our colleagues who can't be here today, Yuan, started talking to the banks, and it turns out the banks have the same problem. They can't share data either, and they would also benefit from it. How do you, for example, identify financial crimes? One bank might see a little bit about financial crimes, but they don't see a lot. Another bank might see something else, but if they pool the data, they could see it. But in this case, they can't pool the data. So can they use this technology? And as you can see now, we're starting to build a whole portfolio of application areas, but the key technology is in the common field here in the middle. We formed a very strong and experienced board to help us with this. And I'm very pleased to say that we have a number of our board members here. One or two of them couldn't make it in person today, so they'll be online in the afternoon. But I'll introduce the board to you here and now, just to, you can see who they are and you can talk to them in the posted session. So I'll start here with Erik Borelf, who is from Vinnova. He's head of the whole AI programs from Vinnova. And with us here at the front line is Mats Moberg, who is our working board member. At the time when this was founded, he was head of R&D for Volvo Cars. Going on towards this part of the room, we have Daniel Gillblad, who is co-director of AI Sweden, now becoming a well-known TV personality here in Sweden, answering questions about AI and also on radio, I suppose. On the same line to here is Brian Reimer from the Advanced Vehicle Technology program, which is heading at MIT in Boston area. And behind here is Dr. Jose Marie Griffiths, who is, she'll shortly be on stage here. She's the president of Dakota State University and very experienced when it comes to cybersecurity issues, which is clearly relevant for us. So that's the board presence we have here, and there's a board meeting this afternoon. So if you want to influence the direction of the consortium, be sure to talk to some of the board members here in the poster session. But the board at the very first meeting told us focus on the central part here. focus on developing the technology that is going to be useful to everybody. That's where we can pull this stuff together. And that's how we get away from this fragmenting that you would see if you don't do it the way we do here. So that's been very powerful input from the board, how to actually make sure that we do invest together and share into the application area. So the presentation is coming up very soon. We'll start here, we'll then talk about some of the overlapping areas, and then we will end with some specific project where you actually take it to application. Now, one of the key things, so this is where we were at the time. And then one day we had a visit from Dr. Griffiths, and she said, what about cybersecurity? Maybe that's something you should think about from start rather than as an afterthought. So I'm going to let Dr. Griffiths talk a little bit about this here, and we couldn't have anybody better to help us guide through this, being an experienced academic leader, leading a major university in the US, and also having been on the National Security Commission on AI in the US to help shape policies and thinking in the government sector there. Brings us a lot of good perspective and a lot of insights that we need to consider here. And that's something that you all can benefit from, learning how to do it. So with that, I'll introduce Dr. Griffiths to give us a quick overview and background of how she came up with the idea of telling us to go cyber. And this was not this year, it was several years ago. So that's something we've actually been doing for a while now.
Okay. Good morning, everybody. I'm pleased to be here and talk a little bit about cybersecurity and artificial intelligence. The interesting thing when I was on the National Security Commission on Artificial Intelligence was there were 16 of us and a big staff of people to help us do research. And they came from all over. And we had everybody's talking about artificial intelligence. And I'm going, what about cybersecurity? So the whole 2.5 years we were working on it. Oh, we did cyber. Let's do artificial intelligence. And what ended up with most of our work was everybody came back and said, we need cybersecurity. So I talk about two different things. I talk about cyber. When I talk about cyber generally, I mean all things computing, telecommunications, etc. And cybersecurity is a piece within the cyber world, the cyber-enabled world. At Dakota State, we have a strong specialization in cybersecurity, heavily based on computer science. And we, in about the same time frame, Mats, when you were talking about creating something here, we started talking about an applied research function at the university. We wanted to work on problems that people outside the university had, would bring them to the university so that our faculty could work and also with our students and work in collaboration with business and industry and the government. So we created a set of labs. We called them the Madison Cyber Labs, but we really call them the Mad Labs, and everybody thinks about mad scientists in our Mad Labs, which is, people can remember the name. And we started off in 2019 when we opened with 9 labs, and now we have 19. And these don't come from me as the president, they come from the faculty and the problems that people bring us. What's interesting about that, I came over initially to a conference on the future of democracy in an AI-enabled world. I think it was, it had a series of conferences on that topic. So a very different non-technical topic in a way. And I met Mats, and we have a colleague in common that we've both worked with. And he said, come and see the Edge Lab. And I said, okay. So I go over and I see the Edge Lab, and my mind is going, this looks remarkably like our Mad Labs. Same concept, same idea. We're working with the external world. These aren't sort of theoretical developments. These are very practical, useful things that we're developing in collaboration with the outside world. And so as we got into our conversation, I'm talking about the labs we have. The Internet of Things. We have a lab called the Patriot Lab. I sit in meetings and I come up with acronyms. What rhymes, what can I think about an acronym for the Internet of Things? Well, I think Patriot, okay, protection and threat research for the Internet of Things, the Patriot Lab, very appropriate for our national security mission. We have the Red Lab, Deep Red Lab, which is a lab that's doing vulnerability testing, trying to break into systems, but not just at the surface. We go sit there for a while and see if somebody's pulling data off over a period of time. That's the Deep Red Lab. We have reverse engineering labs, malware labs, but then we have our other application areas, not just national security and defense. And we have labs in the financial sector, which is very important to our state. We have a major financial activity going on. Financial services, same problem. We have a sort of very, very strong alliance with 2 of our local healthcare systems. So we talk about cyber health. We are recently moved to create applications for our agricultural sector, where agriculture is our biggest industry. South Dakota is in the middle of the United States, very flat, very Scandinavian population. So, you know, we grow wheat and soy and all those kinds of things. So agriculture is a big deal, but hey, agriculture is the same thing. Brian talks about vehicles communicating with each other. We talk about vehicles, agricultural vehicles, communicating with each other, communicating with sensors, and finding out what's happening so that we can improve the delivery of our crops and our food production life cycle. So all of that was going on. And we're thinking, we've also sort of, the last several years, developed several degree programs in artificial intelligence, which emerged out of computer science. So we have exactly the same mix of applications that you do, Mats, here at AI Sweden. And then as you were building out the Edge Learning Consortium, we have the same interests, but slight difference. If you look at the need for security in the AI-enabled world, you need to secure, first of all, people talk about the data, right? Data flows, and we all know about data poisoning. So we can sort of create solutions to data poisoning, particularly the more devices you have out, because in a way you're distributing the intelligences out there. So we need to protect the data. We also need to protect the algorithms. You can attack either one and end up with negative results. So I think thinking about cybersecurity from the beginning as you're developing algorithms and you're looking at how you're going to use training data and then how you're going to use production data, live production data, how do you protect that? There are a number of different ways that you can bring the techniques of cybersecurity rather than after the fact, but you build the protections in from the beginning. And we need to do this because it's very expensive to do it afterwards. That's an area that I thought we could contribute to the whole Edge Learning Lab. So we started off last summer with an exchange program, having our students, some of our students and faculty coming over to Sweden to work with a group of students and faculty here in Sweden. And then they all came back to South Dakota. So it's 4 weeks in Sweden and 4 weeks in South Dakota. And you'll be hearing from Victor a little bit later. He's going to be talking about that and telling you what the students did and what interesting results they have. But this has really grown very dramatically for us. Since we sent our students over, we talked with one of our partners, Case New Holland. Case New Holland develops a lot of agricultural machinery. They were so interested in what we were doing, they funded our exchange program from the US side. Sorry, Victor, and pity we couldn't do both sides, but from the one side for 5 years, okay, just to find out what we're doing. So I do think that this is important, and this is how the collaboration can grow. I have a new one that Mats doesn't know about yet, but the Case New Holland, we came to work with them because they acquired a company called Raven Industries. Raven Industries was based in South Dakota and nationally, well, it's not really so well known. It does a lot of work in aerospace and defense. In particular, they make stratospheric balloons. You probably know in the United States, we now know a lot about stratospheric balloons as we monitored 1 or 2 flowing across the United States a couple of months ago. Well, Raven Industries has now separated itself and it's now called Aerostar. And we're working with them because most of their IT people, researchers are from our institution. So we have another opportunity to work in the space area along with, we also have in that part of the world, the Earth observing satellite system data come down into South Dakota for processing. And that's what feeds Google Earth. So the data comes down off the satellites into our processing center in the middle of the country, and then Google Earth gets the data from us, process data from us. So we're very, very interested in continuing this work. We can contribute a little bit on the AI side as we work on these application areas in finance, healthcare, mobility. We just don't quite call it mobility, but we're doing mobility in all these different areas, and cybersecurity as well. And so we look forward to continually working with you on these problems. I will be doing a poster session, so you can learn more about our 19 Mad Labs and other things that we're doing, and I'm happy to be here.
Thank you very much, Dr. Griffiths. That was an excellent introduction, and you can see by working together, we build on each other, and that's exactly what we're trying to do here in the whole direction. So now you saw the cybersecurity platform that we're trying to put in place for everything we do here. And what I'm going to do now is I'm going to introduce a very good colleague of mine here as well at AI Sweden, Kim Henriksson, who is one of the key persons behind putting the lab in place. So he was the one who ended up getting that empty room you could see in November, December back in 2020, and about a month and a half later had the whole lab up and running, and has been involved in the development together with a number of colleagues, both from AI Sweden, but also from our partners going forward. So what Kim is going to do is give you a very brief overview of what's in the lab. And with that, I'll give you the clicker, and it's the big button.
Okay, thank you. So, good morning, everybody. My name is Kim Henriksson. And for consistency, I have the same clothes as the movie. In order to truly accelerate and enable all the partners when it comes to AI and actually doing something practical, realized we need to have the ability to, together with our partner, offer up environments where you can do experimentation, where you can get the learnings quick, easy, with as low barriers as possible. So the lab really consists of representative hardware, all the way from the edge to what you find on premise or in the cloud. And I just brought up a few examples here really to sort of try and make that point. And we see that for edge learning, it really makes sense to have small units in sort of resource perspective, because they are representative of what you will find in a satellite, in a car, in an X-ray machine, in the manufacturing plant, and then have it connected in such a way that we have real communications, either wired, wireless, 4G, 5G, and so on. And then have the frameworks and hardware representative of on-prem. And what we then do with this is that we want to facilitate these type of learning and explorations. And you can really see this as a multi-purpose, multi-tenant, on-prem cloud type of solution. I know many buzzwords at the same time, but it's all about making sure that partners can, as easily as possible, have an idea, and then just within a few hours, be started with a hands-on experiment with representative hardware in representative environments. If that be virtual or real, doesn't really matter, as long as it's speed, and it's all about that part of acceleration. And I want to give you a few examples here. We have from the public sector, Helsingborg Stad. They're looking into how do you use language models in this case. We have Volvo Cars and others seeing how can they do federated learning in their entire fleet. And one of the one I like the most actually is this one. It's quite small. It's over here in the corner. It's Proact and Swarm Grid that together with the local region is setting up a complete copy of the AI environment that the local university hospital has. And the reason for doing it here is because they want to experiment more in how should you do this more efficiently, how can they share it with others, how can they collaborate. And what we try to do together with them is to reduce the barriers, not only for the local region, but for them to be able to work together with other regions without necessarily letting them into each other's IT system. And they can do it here in this sort of neutral platform. So the goal is really to make collaboration as easy, as quick as possible. And if you want to be a part of that, Mats will tell you more about it right now, I think. Thank you.
Thank you very much, Kim. And take the clicker, thanks. Yep. And the 2 hours, it sounds like a challenge. It's a vision that we hold on to dearly here. It's has happened. We have actually been able to do it a couple of times. And why we have it is that, in my experience, I'm sure in many of your experiences too, when you start a startup organization, it's perceived to be super quick, super agile, super fast. And then as the organization develops and grows, it becomes slower and slower and slower. And I have yet to find the remedy against that development. So we're experimenting here too and saying, well, just keep the 2-hour image in your mind. So as we develop new processes or new agreements or anything like that that we feel we need to put in place, well, how are we going to do that within the 2-hour time frame? So that's just about a way to challenge ourselves and not lose track of the idea that speed and boldness is what we want to do. So of course, there can be things holding us back. We run into it all the time. Things like there might be a queue sometimes on the machines. Now we just got some recent additions. We have good capacity again. There can be some delays on the data side. Sometimes partners come with data sets that we can't just put in there straight away, but we have to sort of approve them so that we don't violate any of the data regulations that are around. So sometimes, we run into things like that, but if using a standard data set that we have pre-approved, wanting to do some clear experiments, this is definitely possible to do. So the big secret sauce, as you would have realized, is the people. It's not the machines, it's not the space itself, although that helps, of course, but it's the people, talents. We focus a lot about giving people a platform for their own career development, because we figure that if we help them, they'll help us, they'll help themselves, and they'll get to experiments on their ideas. They'll learn from other people that they would never meet otherwise. And they would get ideas cross-sharing between application areas, but also between specialities or expertise. We have lawyers working with us, we have engineers, we have scientists, we have people who are working on AI, we have also people working on the infrastructure, just exactly as we had hoped to achieve from the beginning. So we have a talent program, and that's subdivided into a whole bunch of different target groups. Here are some of them. I'll just highlight a few to the crowd here. One is the master's thesis program. Many companies sponsor master's thesis here in the spring, especially. We give them an opportunity to sit together and learn from each other across different companies, again, using our infrastructure, having people here as mentors. We have, I term it mid-career technical. And we have a number of people who are working in companies and are feeling that they want to take the next step professionally and in competence, but they have a hard time to find that in the company, that opportunity. And in a number of cases, more and more now, we're seeing opportunities where people are given a chance to come here part-time or full-time, spend 6 months to 18 or 24 months, even in some cases, at AI Sweden on their company payroll to develop technology and bring back to their company. They bring the problems, the challenges they have, and they bring back the knowledge. And I put a quote up there: the fastest way to transfer knowledge is in the head of a person who moves. It's not on a paper. It's actually somebody who's been there doing it, has both the knowledge and the know-how. And coming in with the company problems and company challenges to us, talking to people, for example, if you come from mobility, you talk to people in healthcare or in space, how do you solve this problem? The bank people come in and ask people in the medical side, how do you guys do it? You have the same problem. And then they find ways forward. So this is something that I personally believe very strongly in. And we'll have a couple of colleagues here. Max, for example, who is presenting last, is an example of one of these mid-career technical people who are here. Then we have people who are very young, who we're giving a chance to grow. We have postdoctoral programs, and then we have Pablo, who's more or less part of that. We have people who come here on sabbaticals from universities. We have the cyber talent program, which Dr. Griffiths just described. And then we have what we call the apprentice opportunities, and our good colleagues here, Preta here in the back and Kaisa, who are out at the front desk, are in the apprentice opportunity, learning together with our more senior technical experts how to set up a lab. And they help us a lot with everything from what we do today. So a big thank you to you, Preta and Kajsa, for being here and making sure that nothing goes wrong. But also going on the technical side and networking, finding potential opportunities for work and so forth. So these are a lot of opportunities, and we respond to partners' needs. So if they want something, training, education, or outplacement, just contact us and we'll see how we can fit that in. But it is all about people, and you can see some pictures here of how it may look in our labs or our facilities. This was a contest. We had some hackathons where some partners came in, and we get students working with professionals, and lots of energy. And when we have royalties and others coming in, we try to send our students in because they do a great job managing the high-level visitors. So with that, I'm going now to move into show you what our talents are doing. And I'm going to start off with Daniel, who is, I'm standing too far away from it, so who is a co-director for all of AI Sweden. So, and he is the co-director of the responsibility for scientific vision. He's been involved with the edge learning establishment here since the very beginning. And I'm going to leave it to you to tell more specifically about how to think about this as a scientist and how to keep technical leadership. So
thank you, Mats. Nice to see you all here today. In just a few minutes, we're going to see lots of examples from lots of these areas of different applications of decentralized AI, actually value creating solutions using AI. But as Mats said, let's just first go through a little bit about the backdrop. Why do we think like we do? Why do we put together these programs as we do? And I think that one of the first things we should step back to is basically a few years ago, we started looking at what are the basic technologies and drivers that will change AI adoption and acceleration, not only in Sweden, because it's going to be the same all over the world, basically. We came up with a number of them. I'm going to talk a little bit about the first one, which is not necessarily decentralized first. And that is a little bit about, you have seen a lot of talk about, for example, large language models and things like that lately. So a few years ago, we also started a program, a strategic program, looking into how is the future of machine learning and shareable models going to look like? Because one of the biggest problems for me as both a researcher within machine learning and as a practitioner is basically we were rebuilding things again and again and again. We had a new problem, we had a new data set, we trained a new model end to end, we built a new solution. It took a lot of time. It just wasn't shareable. At the same time, we could definitely see with the introduction of the transformer architecture, which is going to be basically everywhere in all domains pretty soon, if it's not already, that moving from these end-to-end specific tailor-made applications to building basic representations of certain data sets or data spaces that can then be specialized much quicker and much more with much better precision than just training end-to-end, to actually working with models that we have today, both in language and partly in vision and so on, that can actually answer more open questions than what we had specified in the beginning. Not necessarily specifying everything that the model needs to answer right at the inception, basically. So one of these things that we did was basically saying, okay, language models are going to be first. We need to be part of this. We need to make sure that we have these resources for Sweden. So we started building GPT-3, a large language model for Swedish. It's available now. You can use it. You can build upon it. But it's one part of the complete solution, so to speak. Because what we're also seeing right now is that we need to be able to contribute with data to these types of models, to work together with between organizations that might not necessarily be able to share, for example, language data and so on. And we need to figure out ways to train these large models, to use these large models in a much broader ecosystem, basically. So one of these fundamental things that we started 3 or 4 years ago is already starting to converge with one of the other things that we have, that we're building here right now. And that's looking at these type of decentralized approaches. What if we do not have everything in one place? What if we need to learn in many places or combine models to perform better, basically? So we put together this Edge Lab with the vision of trying to build this type of technology. And I think this image, especially with the cybersecurity backdrop, really specifies how we want to work with these things. Of course, we need to solve a lot of fundamental problems in decentralized learning for foundation models, etc. But by looking at, let's say, a more complete picture from finance, mobility, space, healthcare, and so on, we can actually find out, so what is the actual complete drivers that we need to figure out? AI is a huge space. We can figure out lots of different specific solutions and so on. For example, looking at privacy, looking at security for federated or decentralized learning. But using the practical examples, we can guide ourselves a little bit in which explicit specific solutions we're actually going to use. And that's what we're actually doing here. And I think you're going to have a few examples of that later on. And I think the cybersecurity as a backdrop is also quite essential. We see this is becoming more and more of a problem within all types of AI and machine learning, data leakage, different types of possible adversarial attacks and stuff like that. And bringing that in from the beginning. So yeah, I have also been doing AI and machine learning for networking for a very long time. And in a lot of large collaborative projects, research programs on networking, actually cybersecurity and security was also one of these things that you put on last, right? You built everything, network protocols, network management, everything. And then, oh yeah, we need security. We'll have a work package on security. They'll do their thing, right? It never worked. This will work. And now we have a broad scope driven by real applications that can help us develop these kinds of fundamental technologies with direct real-world usage. So this is a little bit about the backdrop on why we're doing what we're doing and why we're doing it here, together with this speed and boldness statement, basically, that Mats stated earlier, because we need to be pretty quick on our feet. AI and machine learning are basically changing every month now. So yeah, we'll have to move along with it. And with that, I think we'll go into some specific examples and technologies that we are developing here at AI Sweden and the Edge Lab.
Thank you, Daniel. And then there will also be at the posters later on, so you can get more details or more information that way. Now, we have our first speaker from the consortium work, and I'm going to introduce to you now I think maybe it was even our very first project that was done here. And I'm going to ask Dr. Mina Albeginabi to take the stage and give us a tour of what she has done in, I would say, the intersection of mobility and healthcare and space, and probably in this area here. So with that, we'll pass it to Mina to come up here, and I'm really glad you're here to show us. And she will come back a bit later and have a sequel to her first presentation. So.
Today I want to first talk about one of the maybe first practical examples that we did at the Edge Lab, and it was a great collaboration between different partners and AI Sweden. And we did a lot of learning in that project. So it was about how we can do image object detection at Edge using the devices that we had at Edge Lab. So why we wanted to do this project actually? So I work at Zensight, and one of the challenges that we have there in mobility sector is that basically we need a lot of data collected worldwide to be able to continuously develop our AD software. But as we know, more and more countries are basically having more restrictive data regulations, which you need to comply, right? And that means that the current best practice, which is basically collecting all the data in one data center, is not working anymore. Because then basically that approach needs a lot of energy just to transfer all this data in one place, needs a lot of data storage and also a lot of data transfer, and all these processes make this loop be slower than it should be. And also the more important thing is the compliance issue, because from some of the countries like China, we cannot move the data out, meaning that we need to left training on such data out, meaning that we will have less best software, or you need to find a way to kind of comply with those regulations. So we saw that this approach is not sustainable. So what we could do, we found a lot of potential using this decentralized learning. Perhaps you have heard about this in the earlier presentation. So one approach could be that we basically collect data in different data, local data, silo data centers. And then, for instance, in US that have some specific data regulations, one in Europe, like GDPR, and one in China, for instance. And then we kind of do decentralized learning between these data centers. That's the first easiest step, right, to solve this problem. But also the next step, which I will talk about it in the last part of this presentation, is that instead of still doing this, what about if we do basically training directly in the car where the data is generated? So basically it could be even more compliant, right? Because then we are not even moving the data to these data centers. So it could be even more comfortable for our customers and even shorten the loop that we want to improve our software. So we started this Hello China POC because we already see the challenge with Chinese data. And the questions that we wanted to answer was that basically, if we have this cross-silo setting, then could we do this decentralized learning with Chinese data and European data? And what would be the kind of results that we get? Will it be comparable with this with centralized learning, or yeah, basically what we need to do and what are the steps? But the challenge was that because we had lots of partners in the project and we wanted to be as fast as possible, so of course we needed the data, but because of all this and also sharing the data is complex process, takes a lot of time because of lots of complexities you need to consider, which I will talk about it later on. Then we saw that, okay, we can't do this in a timely manner. So what we can do is that we use some proxy data instead. So we can get started just to something that could be similar to basically the challenge that we have. So we used instead this Baltic Seabird data set that was available at Edge Lab already. And yeah, another approach could be that we use synthetic data that Pablo and others, we will talk about it later on, Sylvia. So that could be also another option, but we took this one because it was a real-world data set, kind of a representative of what we had, because the data collection between these data centers could be different. We might collect, let's say, more data in Europe than in China, or vice versa, and so on. And then it was an object detection problem. We had annotations for that, which is one of the challenges that, for instance, in mobility we have, in space we have, and in healthcare and so on. So we started with that. And basically this data was collected into 2 sites. Let's assume Europe and China. So kind of similar. And then we set up basically this infrastructure in Edge Lab, the devices that Kim was talking about. We use those, 2 of those, like NVIDIA Xavier, that we have also in the card. And then basically each of them was kind of a data center representative. And then we use the FEDEN framework and then run the object detection model. I will not go into more details, but what we learned from that project was actually we saw comparable results when we do decentralized learning and centralized learning. And we saw, for instance, if more clients get participated, then we get even more gain from all these learnings together. And also, of course, if a client has less data, when they participate, they get more boost, which is natural, right? Because they get access to more data. And also, we saw that even that experiment, we saw that data poisoning and non-ID could be a big challenge for decentralized learning. I think Kim will, Victor will talk about it shortly about data poisoning later on, but yeah, these are the challenges that needs to be considered in this setup. But after this, which was a great start, we said that, okay, let's take it one step further. What we can do, instead of having silos, what if we go into the car and train the models at the edge, exactly, not in data centers? And we started with this decentralized training of 3D lane detection, which is one of the main perception tasks that is running in the car. And then, yeah, there was a big question mark here that how these models, many of the perception models that we have in the car or other places, they are supervised, meaning that they need data labels with high quality to be trained. So then the question becomes, we don't have a skilled human annotators at the edge. So how we can do that? We need to find automatic solutions to solve this problem, create the training data, and then train on that data. So what we did was that we came up with a fully automatic lane labeling approach. And what was the idea behind that? Doing so, it was that most of the AD cars today are equipped with a map, kind high definition map, which basically have more detailed information than the navigation maps that you see in the car. So they have lane level information, for instance, which we can use. And then if we have the image and also some high precision, localization information from the car, it could be from the localization module running in the car on board, or it could be from more accurate sensors. Then combining these sources together, like different multi-sources, then we could basically get the 3D lane annotations, which we could use for training. How that can be done? So basically, if we know where we are in the world, then we can query this HD map and it's basically GPS coordinates, globally where we are, more or less. And then if having that, then we can query all the lane information around that area. And then we can filter out, because we wanted basically to just keep the lanes which are relevant for the image, right? Because we want to create annotations there. Then we can just do some simple filtering, keep just those relevant information, and then we do some coordinate transformation from this global coordinate to like local, which is the rear axle, for instance, of the car. And then we have the lanes, as we saw before. And then we basically could train some models like this, given the input image and the 3D lane annotations. We could train a 3D lane detection in an end-to-end approach. I will not go into details of this, but what we learned from this project was that basically with decentralized learning with fully automatic annotations, we can get comparable results. For instance, if you look here, we can get more or less comparable results with when we do centralized learning with human, like annotated, highly high quality human annotated labels, or decentralized with that data. So there is a gap still, because you can even do more better job and filter out some of those automatically generated annotations that might not be the best quality, but we didn't remove that to kind of see what happens. And we see still we get comparable results. We don't lose that much, but we gain a lot, like shorten loop and much, we get compute in the car instead of investing a lot in the data storage and so forth, which is a great gain, I think. So by this was done mostly locally, but we wanted to do our collaboration easier, especially with AI Sweden. So we could take the step to share our data finally, which I will talk about it later on. And hopefully more of you use that data set. Yeah.
Thank you so much, Mina. And Mina is a great example of many of the things we talked about before. She is one of the mid-career technical people who's been able to spend time with us at AI Sweden from Zensact. She's worked, as you could see, across many fields, learning and bringing back knowledge. And as you could see, the best way to bring back knowledge is in the head of a person. So Mina is a fantastic example of that. You can also see how some of the examples that she's worked on were things we identified here. Like, for example, automatic annotation. We needed that. So how do we do it? And that's what you could see a result of here. And then that's now available. How would you apply that in some of the other fields that we'll look at? And our next speaker, who is the last speaker before we take a short break, is Dr. Pablo Gomez, who is here also as a mid-technical career postdoctoral position from European Space Agency. He's been working here in our Stockholm location, where we have our main space group, but also working together with a number of the researchers here who came from mobility and health. So I'm going to give it to you, Pablo, to take us through some of the really cool stuff that you have worked on.
Thank you.
It's the big one.
Yes. Good morning. Thanks for being here and having me. So I'm seconded from the European Space Agency from the Advanced Concepts team for a year to research the topic of edge learning. And what I would like to highlight today for you are 2 points. The first being that to get from the research that we have in machine learning, federated learning, many topics like this to actual applications is kind of the hardest step maybe, and the one that we really want to focus on in our research. And the second one being that a lot of the hurdles on that way that we face are actually very similar in different application domains, so that we can translate them to other topics. Now, there we go. So as you might imagine, my work is mostly about space, and one of the things that we find is that there are a lot of ideas what we can do, a lot of applications, but it's very important to consider what the environment in space actually looks like and what the fundamental limitations are that we face. And one of those factors that you have in many applications, be it, for example, the wildfire detection or be it the topic flooding, is that you care a lot about latency. So the time that it takes you from having your observation to making a decision, getting an information on what to do. So this is one of the aspects that's quite critical to model. And I guess it's probably not a big surprise to you that this is not particular to the specific application, because if you're in finance, then latency is quite important to you as well in a very different manner. But fundamentally speaking, if you train decentralized models or federated models, you have to account for it, and it's one of the core constraints that you might care about. Similarly, of course, in mobility, you don't want your autonomous system, whatever kind it is, to be quite slow or to not be responsive. So what we can do is that we try to model these aspects before going to the application to immediately account for them. And this has already for us led to quite a few interesting findings, because we have the setup where this is very early, from half a year ago roughly, we have the software Paseos that we use to model these constraints and aspects. And this is a machine learning model that we trained on 2 simulated satellites. They have similar but different data, and they try to learn a task. And we noticed that one of them was, so the higher is a higher accuracy here, one of them was much better than the other. And fundamentally, they had the same task, and it's the same hardware, everything the same. So the question was why? And what we noticed is that the reason is these vertical lines that you can see here indicate communication between the satellites. And there's a difference because due to the orbits that they are on, they are at different times in the sun, which leads to them training at different times and learning. And so for the one satellite, it would always get a model update and start learning, and the other one had to wait and might get another update and then start learning. And this actually had a profound effect on the speed that they would learn the task. So one of them would always immediately be able to utilize the new model, and the other wasn't. Now, this is something we never expected. This is not something that you would think of if you were doing machine learning research, but it's actually quite a big impact. And this is what we hope to do here, to step-by-step account for these things. And this is what we can do. We can model it in software, and then, of course, come here or remotely log in and use the actual hardware, because that's the next step. Because if you want to do this in real time and to account for the time it takes and the energy it takes and so on, you need to do it on the real hardware. So what we are able to do here is that we have a very systematic approach from going from a very research perspective on a topic to a very application-oriented one that starts to account for a lot of the very harsh constraints you might face. So what I think are the main takeaways here is that this allows you this kind of approach to do very rapid prototyping. I think it was illustrated, I mean, we didn't build this in 2 hours, I'll admit, but of course, it was quite enabled by having this environment. And I think it's essential to take this approach that you step-by-step increase the realism. You cannot go from your research to have a fully fledged simulator accounting for everything, but you can increase the complexity step by step and account for these constraints. And what that gives you is that you have a much lower time to finding the reality gap in your research, because of course we all have different backgrounds and so on. And these topics are very interdisciplinary, so we are not able to in our mind even come up with all the things that will affect us. Like this, I mean, I'm from the space background and I didn't anticipate this problem with the learning on the satellite. And this way we can find it out much sooner and at a very low cost, because we don't have a large investment to take. And finally, the point I personally want to highlight here is so this Paseo software, it's open source, and all the research we do is open. So this gives us a lot of robustness, because we have other people using it who give us feedback, who can tell us, this is maybe not so realistic, or I think you have a bug here, whatever. And this external input is quite valuable, because it's something you wouldn't get if you did this in a proprietary sense and don't share it with anybody. And also it automatically pushes us to enable various applications, because I have one research idea, my colleague has another, and then there's 3 other organizations that have different tasks they want to perform with it. So the whole design of this thing becomes very modular and very useful to a much larger group of people. And I think I don't want to stop you any longer from getting some coffee. So thank you very much at this point.
Right, thank you so much, Pablo. That's another great example of how things can work out here. And the importance of having access to a real lab and some real problems and experiment here before going into application in cars or in satellites. And that's what we were trying to do. If you remember the picture I showed, where you reduce risks and you reduce the barriers because you actually know that it will in all likelihood work. We're going to continue now with short presentations from a number of our researchers who are here. We have also a couple of researchers who were not able to make it. We'd acknowledge them as well as strong contributors, among them Johan Östman, who is away today, but has done a lot of work together with several of the colleagues here in space and other areas. But the first of the block here is going to be Edwin. So I'll pass it to you without further talk from my side.
Hi, my name is Edwin, and I'm a research engineer at AI Sweden. I came to AI Sweden about 9 months ago to do my master thesis in crypto-inspired decentralized learning. And when I came here, I got to meet all the missing people and started working on these cool projects. So when I was offered to stay, it was like no-brainer for me. I was working with Johan Östman, as we said, and he actually fled Gothenburg, the amazing weather here, and went to Greece instead. So I'll try to answer your questions later, but if they are too difficult, I will refer to Johan. But I'm going to talk about graph learning. I'm going to try to introduce this to you. So super simple example I'm going to start with. So here we have a house that we want to sell, and we want to predict the house price of this. This is the data we have. So we have it was built 98. It is 140 square meters. It was last sold 99, and the price was 1.5 million Swedish crowns. From this data, it's quite hard to predict what the house price is going to be, right? Even if we have a large data set, it's going to be hard to train that model and predict from these features. So what we kind of want to do is represent the data in a way that makes the prediction easier. And if we do this by adding all the neighbors and applying the information to them, embedding the information from the neighbors into the house we're trying to predict, this task will be a lot easier. So here we have another house that's very similar. It's built 97, it's similar size, but it was sold 2020 instead for 2.1 million. So it's going to make predicting our house much easier. So you kind of see here that this is represented by a graph. And there's actually a lot of applications or areas where we can represent data as graphs and apply graph learning. So healthcare, finance, mobility. But this is actually also not a great representation, because in reality, this is just part of a global graph, right? So instead, we have this scenario where we have organizations and companies that sit on graphical data with connections between them. And here is where decentralized learning comes in. We want to be able to do decentralized learning on this and predict the nodes, predict connection, classify, stuff like that. And yeah, this is just some examples where we can apply this in. So what we have going on right now is we have a team or a group at Chalmers that we are working very closely with, and a PhD student there is doing research on graph learning and decentralized graph learning specifically. So it's perfect for us because we talk to them. They teach us stuff that we can apply in our projects that we have. So one of the projects, very recent project, is this energy project where you want to predict the energy consumption in these hexagons all over Sweden, or predict or classify. And then you can connect these areas through this graph representation. Another area or another project that I'm working on, and Johan, is this finance project with Handelsbanken and Swedbank, where we have large transactions network, and we want to find money laundering in these networks. The state of the finance project right now is that we can't work with that data because it's sensitive. So we are right now generating synthetic data, and this leads me into my next talk that I'll just go right into, generating synthetic data. So yeah, what is, and especially tabular data. So what is tabular data? It's essentially anything you can put in a spreadsheet, right? So, you know, Excel and stuff like that. You usually have, you can set them in categorical values. So you have like country of origin, Sweden, Denmark. You can put continuous, you can have continuous variables, age, length, stuff like that. And you can have mixed variables as well, like mortgage, for example, house mortgage. So either you have a mortgage or you don't. So that would be 0, or you have a mortgage that can be any continuous value, right? And this can be found everywhere. For in the graph learning example, this kind of data is what's on the node in the graph, right? So why do we need to generate synthetic tabular data? Well, the easy answer is that more data will generate better models. Intuitively, if you have really much synthetic good data, the model that we say we train a classifier will become better, just better than the if we train on just small real data. It's very important when in the case when data is scarce. So if we have anomalies and stuff like that, so we want more of them to better predict and classify. It's also privacy compliant. I put quotations on that because it's kind of fake, right? So it's not the real data. So the GDPR and privacy compliance doesn't apply to it, which is nice for us because we're working with this kind of data. So that synthetic data isn't sensitive. So essentially what we want to do is to, if we have this, for example, this feature right here to the left, we want to create very similar distribution of that feature for the whole data set. And it has some challenges, right? It's difficult to do some stuff. You can ask me more about this in the poster session. For the quality, but also for the privacy, because that was the quotation from before, right? Because we can't produce real data points, because then we have a privacy concern. If we reconstruct the real data again from this synthetic data, it's no good. But there are ways to prevent that. We are looking into state-of-the-art models. So we have GAN models, generative adversarial networks, and also diffusion models. You know, that DALI and Midjourney, right? Generating images. It's interesting because now, like, diffusion's model have almost like won the generative challenge. It starts looking the same in also tabular data. Diffusion models are quite good at generating tabular data as well, even if it's harder. Why do we need to do this centralized? It's essentially the same arguments when data is scarce, when we have heterogeneity in the data, or if we, for some reason, want to collaborate and we can't collaborate. So in the case with the banking, right, they have transactions network, they can't share it, but they have very few anomalies. So in this case, people that are trying to launder money, but they can't share that information. So instead, we want to can make a synthetic generator that can generate money laundering, and we can generate a bunch of money laundering transactions and train on that, and we will have a very nice classifier that can predict money laundering. Yeah. Ooh. Is this working? I have some results here. I think we can talk more about that in the poster session. So that's what I think I had. Yes. Thank you.
Thank you so much, Edwin. So now we're going to continue into on the synthetic data side here. We're going to have Sylvia coming up. Sylvia just recently got her PhD in this area, and she's been working across health and mobility, working also with synthetic data. So first of all, congratulations on your new degree, and I'll give the floor to you to present some of the work that you have done with colleagues here.
Okay. Okay, so good morning, everyone. My name is Sylwia Majchrowska, and I work during that project with Sandra Carrasco. You can see that our surnames are not Swedish. So we are part of A4AI program, which is for international talents. For that program, me and Sandra, we moved to Sweden. I from Poland, Sandra from Spain, and we tried to accelerate the use of AI in different sectors, so healthcare and mobility. So our story starts in healthcare sector in Sahlgrenska University Hospital, and we try to answer the question if AI can help doctors to give the right diagnosis. So the answer for that question is, of course, it can, but. So the problem is the data. So we need to have a very well curated data set when we want to predict, here is the example of the skin lesion diagnosis. So when we want to predict if the person has cancer or not. And usually the internal or even the public data set are not well balanced. It means that the well-known data set, which is ASIC data set, it has only 2% of the melanoma samples. So when I will be guessing and I will saying that every person is healthy, I will have the accuracy of 98%. It's not okay. But the data unbalance is not the one limitation we have here. So in the healthcare sector, as Mina also mentioned, we need to protect our data. So the data needs to be secure because this is the personal data. And also, Edwin mentioned that for the collaboration, we need to be sure that we can reproduce our results for the trust of the AI system. So we need to find some way to share the data, but not sharing the data. And synthetic data is the solution. So also Edwin mentioned that we can create the synthetic images. And in that case, we can create the synthetic moles. I am sure that a lot of you knows the page, this person does not exist. So we create this mole does not exist. The fake mole synthetic data can be shared because this is not the data which belongs to some concrete person. In our study, we used GANs, so generative adversarial networks, with very good performance. So we trained the model only on the synthetic data and made prediction on the real data and achieved 90% of accuracy on the balanced data set. The problem is that still we need a lot of data to train the GAN model, so to create the synthetic data. And here as a rescue came federated learning. We performed 2 different tasks during the Vinnova project. So here we had 2 different hospitals from this region, so Västra Gotland and region Halland. they try to collaborate in two different tasks. So first to generate synthetic data in federated setup. And the second task is the classification between different skin lesions. And we tried with different setups for the classification with different sizes, because usually we have different sizes of the hospitals. And we discovered that the hospital with the small amount of data can benefit the most on that collaboration. But at the beginning, I said that we work not only in one domain. We, in that program, A4AI, we're switching between a different organization. So after 6 months, we switch to the autonomous driving domain, and we just spotted that we have the same problems. So here we also can use synthetic data, synthetic images of different road scenarios. So you can generate the wet road or even the snowy one. And this can help to train then the models to some subsequent task. And that's all from my side. Thank you.
Thank you so much, Silvia. Fantastic. It's a great example of one of the talent programs also that I talked about in the beginning. So now we are going to go back into space again. We have Pablo showing a second example of some really interesting things that's been done here related to the space side. So I have it to you.
Yes, thank you very much. All right, I'm going to focus a bit now on one of the aspects I mentioned before, and quite concretely the dynamic environments. And what I mean by this, I would like to illustrate a bit this time in moving images. So what you can see here is one of the simulations. This is more of a showcase one that we did, where you have two satellites orbiting, and so it's the ESA Sentinel-2 satellites, and they have 3 ground stations. Maybe 4, but these 3 here, you can see the lines show you when they are actually able to reach them. And this is one of the very typical problems that you have, that your satellites are able to communicate to the ground only intermittently. And these windows are not always perfect because you have factors, there are many factors affecting them, and you can only transmit so much. And this is, of course, this problem is not this particular case, right? This is any kind of constellation. It could be inter-satellite links. It can use geostationary relay satellites. You always have these things to account for. And fundamentally speaking, this is, of course, the same in other domains. If you think of the cars, hopefully most of them are not in orbit around anything, but they still have the problem that they're not always reachable, and that you need to communicate, and you need to figure out when and how you can communicate. So this is one of the fundamental things that we also need to account for when we design machine learning methods. And there's several reasons for this. Like, one of them is, of course, that depending on where your objects are, you have different data. So the example I showed before with the 2 satellites, I mentioned they have similar but different data. So this is actually the data they had. They were tasked with identifying 2 circles, an outer and an inner one. But each of them only had half or even less than half of that circle. So the left side here is on one satellite, right side is on the other one. Now, individually, they will not be able to learn this task because their data is very incomplete, or they're not going to be very good at it. And this is a scenario that you can see in many cases in reality, because we had the hospital data just before. The same is true if you have a car that's driving in a specific area that has only particular scenery or roads or road signs and so on. Now, you always end up with this scenario, but then it's also important to consider this when you train, because you need to account from the start for the fact that you're going to have very heterogeneous data. And it gets even more heterogeneous because the problem is not only where you are, but also whether you can communicate. If you think for satellites, the inter-satellite links, for example, they have the problem that they are optical. So depending on atmospheric conditions with the ground, you will not always have a communication window. Similarly, I'm no expert here, but for cars, of course, if you're not in a location where you have a connectivity or connection, then you have the same problems. So at the end of the day, these factors are directly impacting what you're doing. And I think there's 4 points I want to make. The first one being, so these operational constraints, they are quite prevalent. You have them always, be it in the hospital, at the car, or in space. And they directly affect what you're doing. And I think in this regard, space can be quite a good test bed for many things and help. I mean, many technologies were developed for space and used later on Earth. And in a similar vein here, we can see that these very harsh constraints, be it now aspects like power budgets also, can directly help us to build things that work better on Earth. The third thing comes back a bit to the plot with the learning. We see that this directly impacts our performance. So if you make a statement about attainable accuracy and so on without considering these factors, then I would say it would be a good idea to try it with them. Because what we see in our results already, and I think which is also kind of expectable, is that these factors can be so important that they can make or break whatever you are doing. So it's extremely important to account for them early on. And the final point I want to make here is, so dynamics can offer opportunities. What I mean by this is that, so if you take, for example, Sentinel-2 satellites, there's a popular data set called Euroset, which gives you its classification task. Now, if I'm a typical machine learning practitioner, what I will do is I take it, I shuffle it, and I train with it. Now, in reality, this is of course not what would happen, because your satellite is not randomly acquiring images all over the world. So what you would have is that you would see specific regions, right? Now, these images are actually geotagged. So what you could do, or what you can do, is you take the geolocation data and actually create a training pipeline that simulates the way that you in the real world would collect this data. I mean, this is similar on a car, I guess. It's a bit easier if you collect your data while driving. For satellites, we're not yet at that stage, but this way you can, by accounting for these dynamics, get back to the way that you acquire data and train in a much more realistic fashion. And yeah, that's it for me here. Thanks.
Thank you so much, Paulo. Huge contributions here to the consortium from all the work you've been doing. Now, our next speaker wasn't able to make it here. She had to cancel her participation at very short notice. So I will try to represent Dr. Helena Linge, who is working at our node in Lund in South Sweden. She is coordinating all the healthcare activities right now. And this is an example of what has been done here as one of the early projects, also in the decentralized area. The challenge here was to train a model or explore how to train a federated model between two Swedish healthcare providers or healthcare systems. So it's Region Halland and Sahlgrenska Universitetssjukhuset here in Gothenburg. It started off with a proof of concept just to see how the communication would work out between the two regions and the two hospitals, to set that up. Then the next step was to explore how to train using open public data sets, because of course, the same as we've heard from everybody else, we have the issue with confidentiality and privacy and so forth. So just to make sure that everything was working and that we could get it to work, that was the step taken, to use public and open data sets that were approved from all compliance perspectives. And then once we knew how to do it, we had developed the know-how, we've seen that it worked, moved on to identify the real data set, what kind of data to train on, and what models, model architecture to use for this training, and then actually train on real data, where Sahlgrenska trained on their data and Halland trained on their data, and then went on to federate it. The outcome was a very successful project. We were lucky to also get involvement and support here from, in Swedish called IMY, Integritetsskyddsmyndigheten, which is the data protection agency here, who took this as an innovation case and worked with the teams here to explore how would this come from their perspective when it comes to compliance with all kind of data regulation protection. They've just issued a report that's available on their website, and they helped quite a bit. They said a very promising direction. It seems to do what you say. And in this particular simple example, the key concerns identified were related to attacks. Because that is something that some adversarial entity could potentially, if they knew how to do it, break in and access some data. So that brings us back again to Dr. Griffith's presentation as to why we need to think about cybersecurity from the beginning. So the next steps in the project, as you can see here now, is to develop a further understanding of looking at these risks. finding strategies to reduce the probability of successful attacks, and then testing that, see that the next setup actually can hold off such attacks, and then share how to do it once we develop this new knowledge. And there's a lot of interest now across regions who are all partners here at AI Sweden. And then, of course, what we learn here can then be applied, for example, to cars or to satellites, which could also be susceptible to such attacks. So she apologizes that she couldn't make it today, but that's she's clearly available, can answer questions if you contact her directly through AI Sweden in Lund. Now, moving back again to Edwin, who is going to talk about the banks into a little bit more detail.
This is actually the project that kind of ties together synthetic data and graph learning, and that me and Johan is working on. So this is a Vinnova-funded project going on for 2 years. It started February, and it's with AI Sweden, Handelsbanken, and Swedbank. We also have interest from other parties, Bank of International Settlements and so on, and other Swedish banks as well. And the challenge is to find money laundering transactions in Swish transactions. So Swish is the system that we use here in Sweden for mobile transactions, that you can send money with your mobile phone. And the goal is to prevent illegally obtained money, right? So we can stop criminals. It's an estimated 130 billion Swedish kronor is laundered every year, so it's quite a lot. There are 12 banks connected to Swish, and then, yeah, you see some statistics here. 8.5 million Swish users as the end of 2022, 460 million Swish payments, and the volume was about 280 trillion Swedish kronor. And this is cool because this is the kind of first project or collaboration between Swedish banks, and we are actually like having 2 banks sitting and trying to figure out how to be better at finding money laundering, which is exciting. So it's first of its kind. The roadmap for the project kind of has 2 tracks. So the first track is working at AI Sweden and also with the banks and working with synthetic data, because the data is sensitive. The banks are not allowed to share the data with AI Sweden and with each other. So, and then it's about proof of concept, right? Can we make this work? Will we gain value from this? The other track that is kind of in a parallel at the same time is actually testing on real data, and hopefully we can do this. So this is the states that we are kind of are at right now. So for us, we need to generate this synthetic data that is real enough that we can draw some conclusions out of it. And the second track is that the banks need to set up test beds and make sure that they are able to do this and in a secured manner, right? So I put this slide in. It's quite a lot to see, but this is kind of the stage we are on the first track. So here I have generated synthetic data out of. So we essentially have 12 banks here that are connected to Swish, and this in the middle is the transactions network. So this is all the accounts and transactions that goes between them. We span over just about 11 days, so it's not a lot of transactions, 3,000 transactions, and 10 of these transactions in here are laundry transactions. So quite challenging to find those, but we're working on that. But this is kind of the stage we're at right now. Exciting to work with. Yeah. Okay, that was it. Thank you.
Thank you, Edwin, and more questions to Edwin in the poster session. And at this point, you've seen that data is very important. We've had a major contribution by one of our partners, Zensact, who has spent quite a bit of effort and investment on developing a entirely new data set that has just been released. And project manager for this has been Mina, with all the experience that she's gathered here. So she's going to come and explain to you a little bit about what she and a number of the colleagues, some of them in the back of the room here, have been accomplishing. So with that, I'll give it to you, Mina, to introduce a very unique data set available for our partners and others.
Going back to kind of the story that I talked about before. So we wanted to do this for a while, right? It started basically from that FedBird or Hello China project. But as I said, there was complexities and it took time. But it's happening now. So we have this Zensact open data set. You may wonder, what is this? So it's a larger scale, multimodal, and very diverse data set for autonomous driving. So it's one of the basically largest AD data set currently, and it addresses one of the gaps that we have already in other data sets, which is basically lacking the European support for European data. Others just maybe have data from a very few handful cities in Western Europe, like just Germany. But now in this ZOD, as you can see here, the coverage, we are basically having data from more than 14 European countries. And this data have been collected over 2 years. And it has been carefully curated to kind of cover different diversity aspects from different locations, geographical diversity, road types. It covers highways to urban areas to rural roads. And also it covers different weather and lighting conditions. So we have data from snowy parts of northern Sweden to sunny parts of Italy to busy areas driving in Paris and so forth. And one very unique feature of this dataset is it has the highest range and quality sensors in comparison to other datasets. So basically, I will talk about it more, but this is very important if you want to have long range perception algorithms which are needed for high speed driving, because without that, then you can't drive as fast as possible because of the uncertainty. But it's not all. We have also a significant amount of detailed and multitask annotations for different perception tasks, all being high quality, manually annotated data. And also a very nice feature of this data set is that it has a very permissive license, allowing both research and commercial use, which is pretty unique. Most of the data sets just allow you to use research purposes, which basically means that it could be limiting for people like me who are active in industry, so, which could limit basically the collaborations or the acceleration of AD. But by this permissive license, we think that it can open up new opportunities for everyone active in all sectors to solve these unsolved challenges. And of course, to enable this, we had to anonymize the data because of all the compliance and also our willing to basically protect every individual's road user's privacy. And we did basically do it in 2 ways. We blurred faces and license plates and also replaced them with synthetically generated data. This was talked about in other projects as well. So I talked about the sensor suite and also that it has very high quality. So what it contains is basically we have data from high resolution LiDAR sensors, front looking and two side lookings, and it's very like dense in comparison to other LiDAR sensors in other data sets, like we cover up to 250 meters in front of the car. We have a camera, an 8 megapixel, which is very unique, with wide field of view. And we have also high precision, like a positioning sensor. But in addition to that, we are also having some vehicle data, which could be interesting for some other applications, like, for instance, planning and decision and control and so forth. So, for instance, we have a steering angle, and brake ratios, and things like that. In addition to that, also we have consumer grade GPS, which is a very important sensor for things like localization and this sort of applications. And then going back, so we split the data into 3 subcategories. We call them frames, sequences, and drives. And each of them has unique kind of purposes, but all more or less are the same, and part of this data set. So frames, which is really a large number, like 100K. We have the single images, which are all annotated for many different projects, and we have supporting data like LiDAR and GPS and so forth that I talked about around this key frame. So it's mostly useful for perception tasks and things like that. We have sequences, which each are 20 seconds and contains all the different sensors that I talked about. And we annotated also the middle frame for sequences. But we are going to extend it with also temporal or sequence annotations to cover more applications in future. And we have drives, which are uniquely designed for like application that need longer, basically data, like localization and planning to see if it has the effect and so on. And here you can just get an idea of how diverse is our data set. So basically we have scenes from crowded city, night, snow, foggy and heavy rain, and all these scenarios are covered. And you can see how the density of our LiDAR point clouds are and how far we can see basically, which is pretty unique in this open data set. Here you can see like just a glance of the annotations that we have. So we have semantic segmentation of lane and road. We have like bounding boxes for dynamic and static objects, and more than that. Also, it's one of the richest like traffic sign recognition data sets. And beside that, we also provide a software development kit to get a rapid start with the data set. So users don't need to spend their time like preparing or getting to discover how to use this data and so on. So they can just look at our software development, get access to the fundamental functionalities, something like this, that do basically all the coordinate transformation, like for instance, GPS onto the image or onto the LiDAR data and so on. And also we have support for lots of visualizations to get to know the data, and also lots of tutorials and examples are all covered in this SDK that we provide. And of course, it was a very like a collaborative effort. It was a mixture of people that contributed in this project. And of course, you are very welcome, everyone, to do more. There are a lot to be done, and we just get started. So And we are using already this data, even if we are releasing it this week. But we have started using it in some research project. And Christopher will talk about, for instance, an example of that example. And check out our website. You can find a lot of information there, and also can just request access for this data set. Yeah, thank you.
Thank you so much, Mina. Fantastic work by you and the colleagues. And what we're going to take a look at now is that the team has done the groundwork. We have a project together between a number of the partners, Zensact, Volvo Cars, and AI Sweden on federated fleet learning. And we have the head of this project, Christopher Gilberg, who's going to come here and give us a very brief overview of the project, what we're trying to do. And it's pretty early in this project, but I'll hand it to you, Christopher, to introduce yourself and the project.
Thank you. All right. So I will try to keep myself quite short. I think there will be some repetition of what has been said already by other presenters. So I'm Christopher, and I'm a product owner for Fleet Insight at Zensact. And I guess this was shortly mentioned already by Mina and probably before as well. That, but for those of you that don't know Zensact, we're a subsidiary of Volvo Cars, and the purpose of Zensact is to develop active safety solutions and autonomous driving for the automotive industry. And Fleet Insight then, what is Fleet Insight? Fleet Insight has been a buzzword emerging a lot in the last decade or so. And it's essentially all about collecting data from the production fleet, enabling this modern software development where you have a data-driven models instead of having a more traditional way of building your software. And yeah, as Mina mentioned, utilizing the production fleet to collect data is a huge enabler to develop a much better generation of software. So let's see if we can change the slide. Now, yeah. So right now there's a huge transition in the automotive industry, both for going into a more electric platform, but also having a purely software-defined product. That is a big transition in the industry ongoing right now. And with that, we get completely new sets of products where we have central compute that is order of magnitudes more powerful than previous generations. And with this central compute and a lot of, yeah, it brings a lot of new possibilities that we can do in the fleet that we have not been able to do before. This is a picture of the development vehicles that we use at Zensact, and this one, of course, has a lot of extra compute, but also for the production vehicles that will ultimately go to our customers, will also have a very impressive compute compared to the vehicles that are on the roads today. And collecting then all this data that Mina showed a little bit about, with that comes, of course, new type of challenges. When you have collecting raw data, raw vision data, for example, out in the street, and we don't really know what will be in those images. There is a risk that we collect a lot of data that is sensitive, not only sensitive for personal data, of course, but also that we might collect data that is not allowed to be taken in a specific geolocation, so military objects or any objects that are very sensitive from a national security perspective. It's hard to make sure that we don't collect that. So it's a natural challenge that we spend a lot of time and effort trying to solve how we can avoid collecting that data in the first place. And I can also mention that looking back now with the big tech companies growing for the last decade or two, it's often been all about collecting that data from me as an individual, trying to understand who am I, map my behaviors, and try to utilize that and sell that information. But at Sensact, this is not what we want. We're only interested in the product. We're interested in the cars, and we want to save lives in real world applications. But we're not interested in the person sitting behind the wheel. We're not interested in the person walking down the road. It just happens to be the consequence when you collect a lot of camera data in real world accidents that you happen to get also this personal information. So we just want to avoid that or anonymize that data in some way. And here is really where federated learning comes in, because if we can avoid collecting that data in the first place, of course, we will not collect that sensitive or personal data as a direct consequence. And of course, there's also a lot of the other benefit is, of course, from an economic standpoint, because we're collecting a lot of data, and what we see is that there's really no upper limit on how much data we can collect. The more data we collect, the better the system performs. And of course, at the end of the day, this is all about saving lives. So we want to collect as much data as possible without being sort of held back because of this personal data or problems that occur. So with that, we have, let's see if this is going to work. So with that, we have an ongoing research project here at AI Sweden together with Volvo Cars and Sensact, which is also supported by Vinnova. And that is all about taking early examples or use cases for autonomous driving in ADAS systems and try to explore how can we use federated learning for certain type of applications. Can we apply it on a small subset of the deployed stack? Can we use it for a larger part of our perception stack, etc.? A lot of these very fascinating questions. And of course, how can we deploy this and use this in a production fleet without violating the otherwise safety sensitive data that is running on the cars? So to what extent can we use this when the car is running, and to what extent can we use it when the car is not running, and so on and so forth. And I can just end with saying that for us, using AI Sweden was a very natural center point for this research project, because I think it's a common thread now in the presentation. It's a lot of different domains, but at the end of the day, we share a lot of common challenges. So having access to AI Sweden, we are able to explore this technology and research it in that, but also getting help and inspiration from other domains as well. So for that, I'm very grateful. Thank you so much.
Well, thank you, Christopher, and a great presentation of what you guys do and what we do together. If I can take the clicker. Now we're coming up towards the final presentations here. We have first Victor, who is going to tie a lot of it together with some work we're doing in cybersecurity, as Dr. Griffiths was saying in the beginning. And then we're going to end the session here with a presentation by Max on what is coming next. That's a project we're starting up. We're in the pre-study phase right now, but I'll leave that to Max to have as our last presentation after Victor. So with that, I'll introduce Victor, who also started here in one of our talent programs, and then we picked him out to continue working with us. And I'll let you talk about your work.
Yes, hello. My name is Victor. I'm a research engineer at AI Sweden, and I'm here to talk about cybersecurity challenges in decentralized learning. Decentralized learning, cybersecurity is very important in decentralized learning because in its nature, decentralized learning allows for participation by actors who might have the wrong intentions when they enter to collaborate. And this provides new, relatively unexplored cybersecurity challenges that needs to be addressed. So the two main challenges that people are looking at is keeping the data secure and keeping the model safe. The data needs to be secured because research has actually shown that model parameters, by simply looking at model parameters, you can extract information of what data was being used to train the model, and handling this or preventing this is really important, especially if you're working with sensitive data. The model also needs to be safe against attacks or failures in the pipeline. So, for example, research has shown that a single adversary in a decentralized learning system is enough to completely deteriorate the global model, and faulty sensors or some errors somewhere in the pipeline can send faulty models back to the server. That also needs to be prevented, because that can also ruin the decentralized learning system. So now I'm going to talk a bit about how we at AI Sweden have addressed these challenges. So we have a couple of collaborations where we are looking at these challenges. One of them is with Cambridge University, where we are working with the machine learning system labs, which is led by Professor Nicholas D. Lane. In this research, we have investigated decentralized learning, where a subset of the participants are trying to hurt the training instead of contributing. And the results from this research is we have proposed a reweighting scheme where we evaluate the clients and reweight their contribution based on performance. And we have submitted a paper to US Enix Security Symbiosis that has just now been reviewed positively. We also have a collaboration with Chalmers and TU Munich, where with Chalmers we have actually an extended research group that is led by Professor Alexander Grael at Chalmers and Dr. Johan Östman here at AI Sweden. And they are investigating multiple perspectives to cybersecurity in decentralized learning. One of their works is also looking at both data security and the trade-offs between data security and keeping the model safe against attacks. And they have also a paper submitted to Neuralinks and is currently being extended, the method. And then Dakota State University, you already heard some about the program we have, the industrial immersion program, but I'm going to talk a bit more about it. So first, some background. I started here at AI Sweden in the first iteration of this program last year. We were a group of 5 students investigating security in decentralized learning. And it was a really great experience. We got to meet a lot of leaders in the industry and the partners, and really got to learn a lot, and had some great results from that program as well. I think the majority of the students participating has actually continued working with security in decentralized learning. So I would say the first program was a huge success. Now over to this year, the program has grown. We now have 4 program partners: Volvo Cars, Sensec, Case New Holland, and the Next Generation Infrastructure Project. We also, similar to last year, have the cybersecurity expertise from Dakota State University. They are actually reputed to be one of the leading universities in cybersecurity in the US. So with all this together and a really large and talented application pool of students, I'm sure this year's program is going to be a huge success as well. If anyone is interested in maybe hosting a team, we have flyers at the poster for next year. And I want to finalize this talk with talking a bit about knowledge sharing, about my perception of how this has affected me here since I first came. So you heard the slogan a lot in the beginning: invest together and share with many. And for me, since I came here, I have been able to share knowledge and ideas and get knowledge and ideas from all these partners who have been investigating similar subjects as me, and this has made great work to be made, I would say. So that's all from me. Thank you.
Thank you so much, Victor. Fantastic job. And Victor is now the project leader for the industrial immersion program for cybersecurity students this year. So he's taking what he learned last year and helping us do it right this year. So with that, I'm going to introduce our last speaker, who's Max Pettersson. He's another colleague who is here as a technical mid-career person, allowed to be here from his employer, Volvo Cars. Max is working with us in the data factory, and he is leading a pre-study right now that he's going to talk to you about. So with that, I'll hand it to you, Max.
Yeah, thank you. Do you hear me? Yeah. Let's see. Yeah, I will talk about a pre-study. It's a project that we hope that will kick off in a week or so. But first, before I talk about the project, we need to have a little bit quick repetition about what is a foundation model. So this is a model that is not trained for a specific task, but is trained for be more generic. That means that size matters in this case. So often they become quite big. One example is, for example, GPT-3 or 3.5 and 4. This means that you often need to have more or less, you need to have heavy duty machines, more or less an entire data center to be able to train. And it also needs to be quite homogeneous environment, both for training and inference. On top of the foundation model, you add your applications that you tweak to be more task specific. One example is ChatGPT. So that's an application on top of the foundation model. But it's not only for language models, it's also for code generations, drug discovery, text to image, and more. So it has lots of different applications or domains, you can say, that it's very suitable to use foundation models. I even heard an idea of using vehicle data and build a foundation model on top of that. That might be a successful thing to do. So what we figure out when we looked at this today is one big issue is that you need to have a homogeneous environment. It's also when we have now created this GPT-3, the Swedish or Nordic language model, we also see lots of issues with security and privacy related issues that we're not allowed to train on all the data that we want to train on. So our ideas are a little bit think about how to do it, and we will try to do it with knowledge and resources from our partners that are suppliers, that we want to try to create, to find out how to build an infrastructure that help us a little bit with our issues that we have identified, but also with help from potential users with use cases and requirements. So we build the right stuff from the beginning. And what we try to do then is to mitigate those issues that we identify is hardware agnostic. So we can utilize the infrastructure that we have today, make it more secure, add on, of course, because it's us from AI Sweden, distributed learning, but that it's probably is a way of solving the privacy issues, that we can put the training where the data is. So we don't need to bring in the data to a central place. And also make it more scalable, so we can scale it with all the resources that we have available. And we will be out in the poster session if you want to have more information. We also now, previously, before, or right now actually, we're also creating a state of the art about infrastructures for foundation models by Chiara, sitting down there. And it will be in the end of May. You can order it for a small fee, I would say. That's all.
Right, thank you. Thank you so much, Max. And that's a great example of what you could see how we have users working together with the manufacturers of the hardware. As Max was showing, you had companies like Volvo Cars, like AstraZeneca and others working together with the NetApps, the Intels, the HPEs, the Dells, and the cloud providers like Green AI Cloud and Proact and Ixia and what have you, so that you can actually see now how that original vision we had in 2017 actually works now in an example like this. So with that, I am going to sum up and hope that we have been able to show the breadth of what we do and how we leverage technology across all the different sectors. Many of you come from partner organizations, universities, public sector, or industry. And if you are a partner already on the list here, you're welcome to come here and join any of this or initiate your own projects or collaborations. If you're not yet a partner, you can become a partner. You can read more about it at the AI Sweden homepage. There is a link here, and you can go in through ai.se and then just push partnerships to get you there. Helena and I will also be out at the poster session, and if you're here physically, you can come and talk to us here about how to become a partner if you are interested in that. And I also, as the very last slide, like to draw your attention to my.ai.se or my.ai.se, which is a social network that we've created here for people working with or in the area of AI. It's not limited to Sweden, it's free, it's not limited to partners, it can be anybody joining in that. So go into my.ai.se and create your own account, free account, and read the use cases, look for opportunities, look for collaborations and other things. You can get newsletters from us, and also if you want to see what actually happened at AI Sweden in total last year, we have a very new impact report that shows all the other things that are done here at AI Sweden, not only what we do here in Decentralized AI. So with that, I would like to thank all the people online who joined us, and I of course want to thank the colleagues who have made this possible here, not least Kajsa and Treta, who's been doing all the groundwork, but of course all the presenters who've spent several hours preparing, try running, preparing again and dry running again to make sure that we had the material available, and of course everybody for coming here. So with that, I'll sign off the transmission.